Our topic for this week is heat engines. And before we get into too much detail about what that is, let's look at some common energy conversions. So for example, last week we talked about nuclear power, and we go from nuclear energy to thermal. So that nuclear energy basically heats up water, and that water drives a turbine, which is a form of mechanical energy. And finally, that turbine is hooked to a generator, which produces electrical power. So we have this multi-step energy conversion. Sometimes you'll see kinetic in between thermal and mechanical. For this lecture, we're just going to consider that part of mechanical. But once we go through some other energy conversions, notice how often thermal, mechanical, electrical shows up. So for example, if we're burning fuel such as natural gas, we start with chemical and then thermal, mechanical, and electrical. And then we've got geothermal. Geothermal starts with thermal, mechanical, electrical. We've got solar thermal. Everything from the sun starts with electromagnetic. And then thermal, mechanical, electrical. If we're talking about photovoltaics, direct solar, we start with electromagnetic. And we go directly to electrical. With wind, we have mechanical energy. Depending on how far back you want to go, all wind energy comes from the sun, but most things come from the sun that we're talking about. So mechanical to electrical. Hydropower, gravitational potential energy, water falling, to mechanical, to electrical. But notice how often thermal, mechanical, electrical shows up. That's kind of what we're going to talk about today, is how can we extract energy just from heat and produce electricity. So as a lead into heat engines, I'm going to describe to you a famous experiment done in the 19th century by Joule. So this is the guy that the metric unit of energy is named after, 19th century. So he had this large tank of water, and inside the water there was a paddle wheel. And that was attached via rope to a pulley system. And attached to the other end of the rope was some weight. So he basically allowed the weight to fall under gravity, and he had a thermometer measuring the temperature of that water. And you notice that as the weight fell, the wheel would turn and the temperature of the water would increase. So in effect, he was demonstrating the conversion between mechanical energy to thermal energy. Following that, someone named Carnot asked the question, can we do the reverse? Can I convert thermal to mechanical energy? And the answer is yes, and the machine that does that is called a heat engine. So a heat engine is just any device that can convert thermal energy to mechanical energy. Now it's important not to confuse a heat engine with a heat pump. They're not the same thing. So what a heat pump does is it moves thermal energy from one place to another. It doesn't create it or transform it into another form. And this is why heat pumps, you might think of them as being over 100% efficient, but it's not really an efficiency they're measuring. They're measuring how much of some small amount of energy does it take to move a larger amount of energy from one place to another. They're not creating that energy, they're just moving it. Whereas a heat engine, you're actually doing a conversion. You're converting heat to mechanical work, which can then be used to drive a generator if you desire to make electricity. Now, there's a very useful diagram that we can use to describe heat engines, and I'm going to draw that for you now, and you should practice drawing it yourself because a lot of problems from the homework will be based on that diagram, and same goes for the exams. So at the top I've got some heat source. I'm going to call it QH. So Q is a symbol that we use to describe heat. And by the way, I'm going to describe for you first the energy side of the equation. So this is energy. So I've got some hot source, any heat source, and I'm transferring that heat to two different places. The output of the heat engine is just mechanical work, so we call that W. And some of the heat has to be rejected to a cold sink, which we will call QC. So it's impossible to get 100% of the heat to transform to mechanical work. There's always some losses involved, and those losses are dumped into this cold sink. So all we need is a temperature difference between the QH, the heat source, and the QC, the cold sink. If we have a temperature difference, we can extract useful work out of the machine. We also have the power version of the equation. So at the top I have QH dot. And the dot above a symbol just means how fast is that quantity changing over time. So here I've got energy, here I've got power, because remember, energy over time equals power. And the diagram has a similar shape. Some of the power gets lost to the cold sink, Q dot C. And some of the power is output as useful work. That's P. So because I have these diagrams, I have energy on this side, power on this side, and I have this equation, I can write time in the middle, T. And notice that I can go from this side of the diagram to this side via time. So for example, if I take QH and divide it by time, I get Q dot H. So going from left to right is division. Similarly, I can go from the right side to the left side by multiplying by time. So I have Q dot C times time gives me QC. So if I go from right to left, it's a multiplication. So if I know these three quantities in time, I can always find the other three. Or if I know these three in time, I can find these three. So I have three numbers here, one number here, three numbers here, that's 7 total. There's two other numbers which can be used to describe the heat engine, and that is TH, capital TH, and capital TC. These are just the temperatures of the hot source and the cold sink. So TH is the temperature of the hot source, TC is the temperature of the cold sink. Now, as we'll see in a little bit, if I know those temperatures, and this is an ideal heat engine, I can determine the efficiency of the heat engine. And we often abbreviate efficiency as a Greek letter called eta, and it looks kind of like a curly N. So that's our symbol for efficiency. It's just another Greek letter to know, like pi. So if I know the efficiency, I can also place that on these diagrams, because remember that my power output is only part of the heat source. The rest goes to the cold sink, because no heat engine is 100% efficient. So if I have some efficiency, I can write that on this line. And if that much percentage of useful work is being output, I know that my waste is 1 minus the efficiency. So I can write that down here, 1 minus efficiency. And I can write these symbols on the energy diagram as well. So efficiency goes here, and 1 minus efficiency goes here. So it's very important when you're doing the homework and the exams to understand this entire diagram and the relationships between all these quantities. I'll come back to the temperatures, but for the efficiency side, we can see that I can write some equations for efficiency here. I have work, my work output, divided by my energy, which is QH. That's my energy input. Gives me my efficiency. So you can think of this as the energy out divided by the energy in. Gives me efficiency. I can do the same thing on the power side. Power out, which is P, divided by the power in, which is Q dot H, is equal to my efficiency. I can also see that if my QH is coming in this way, it splits off to W and QC, therefore QC plus W must be equal to QH. So I can say QC plus W equals QH. So just by understanding these diagrams and labeling them properly, I can see various equations that relate to these quantities. So what you want to be able to do on the assignments is to solve for the unknowns if I give you the knowns. So if I might give you QH and W and the efficiency and one of the temperatures and maybe time, and you should be able to find everything else just from these relationships. Okay, so now we want to see the relationship between efficiency and temperature. So we have efficiency versus temperature. And remember, for today we're talking about ideal heat engines. So we have this relationship between efficiency and temperature. Efficiency is equal to 1 minus Tc over Th. And this efficiency is essentially meaning that no matter what we do to the machine, if it has this temperature for the cold side and this temperature for the hot side, the efficiency will never be greater than that, 1 minus Tc over Th. There's a couple rules we have to follow. Those temperatures have to be measured in Kelvin. And remember, for Kelvin, we don't use the degree symbol. We can always convert between Celsius and Kelvin. So I have degrees Celsius plus 273.15 equals Kelvin. So I can always go back and forth between Kelvin and Celsius. So this efficiency, the maximum efficiency of the heat engine, is known as the Carnot efficiency. Again, it's the maximum efficiency of a heat engine. So let's do an example. Let's say that I have some process that's producing heat, and let's say it's at 300 degrees Celsius. And let's say it's rejecting heat to the outside air, and let's say that's 20 degrees Celsius. So if I want to find the efficiency, I need to first convert those temperatures to Kelvin. And I get 293.15. And my TH would be 573.15. That's going to give me about 49% efficiency. So if I have this heat engine hooked up to a hot side of 300 and a cold side of 20 in Celsius, the maximum possible efficiency I can get from that heat engine is 49%. Now in reality, you're going to get much less than that because of various losses in the system. But for the purposes of our homework, we're going to consider all of our heat engines to be ideal. So this is how you find the efficiency of those heat engines. On this page, I've summarized for you the equations that we need to know for heat engines. So I've got the efficiency equation, 1 minus Tc over Th, that's our Carnot efficiency equation. It's equal to the work output divided by the energy input, which is QH, also equal to the power output divided by the power input, Q dot H. I have these equations which describe the heat flow in the system. QH is the work output plus the reject heat, and Q dot H, that's the input power, is equal to the output power plus the reject power, Q dot C. All of those quantities are related via time, like I showed you on the diagram. Just divide by time to go from power to energy. To go from energy to power, you divide by time. And I've got the waste percentage, which is 1 minus the efficiency, is equal to my waste heat divided by the heat input, or my power waste divided by my power input. So if you understand all of these equations, you basically understand most of what you need to know about heat engines. Now, one thing I should mention is that a very common mistake for students to make is to confuse this W here for watts. It's not watts, it's not a power measurement, it's work, which is the same units as energy. So I could measure work in kilowatt hours, but not kilowatts. So try not to confuse the capital W when it's meaning work and when it's meaning watts. You'll just have to be able to tell from context which is which. Next, we want to discuss some important thermodynamic cycles, and these cycles are the primary means by which we generate electrical power. So we need to understand some vocabulary first. We've already talked about temperature, capital T. And many of these systems we're discussing, these heat engines, are made up of gases, but we're primarily dealing with ideal gases in this class. So properties of gases we need to deal with. We've got temperature, we've got volume, how much space does the gas occupy, and we've got pressure. Now the ideal gas law states that essentially if I have some pressure of gas and some volume, and I divide that by temperature, that no matter what happens to the gas, that remains a constant. So if this has to be a constant, if my pressure goes up and my volume stays the same, my temperature also has to go up. Otherwise this wouldn't remain constant. Or if I increase volume and keep temperature the same, then my pressure has to go down to keep this constant. So any of these variables can change in any combination. a lot of the processes I can do to gases keep one thing constant of these three, and we have special names for when that happens. So for example, if I keep temperature constant, we call that isothermal. Iso just means same. So if I keep temperature constant, I'm changing just pressure and volume, so I have an isothermal process. So that's constant temperature. If I keep pressure constant, it's called isobaric. Constant pressure. And if I keep volume constant, it's called isochoric. Constant volume. Now there's another special term we need to know, which is called adiabatic. So adiabatic means there's no heat exchange between the gas and the outside environment. Now it's important to realize that adiabatic is not the same as isothermal. Here we have constant temperature, and here we have no heat exchange. Heat and temperature are not the same thing. They're related, but it's important to realize that this can happen with a change in temperature, and this constant temperature can happen and still have a heat exchange. So these are two different processes. So here's an example of a thermodynamic cycle. It's called the Carnot cycle. So I begin at point 1, and I'm going to have a 4-step process. So from point 1 to 2, you can see that I'm going along this line, which is a constant temperature line. I have volume on the V on the x-axis, and I have pressure on the y-axis. So my volume is increasing and my pressure is decreasing, but my temperature remains the same from point 1 to point 2. So point 1 to point 2 is isothermal. And now I have point 2 to point 3. I'm decreasing in temperature, and I am increasing in volume, and I'm decreasing in pressure. So I'm changing P, V, and T, but there's a special effect happening here, which means that my heat is not being transferred with the outside world. So this is an adiabatic process. Now from point 3 to point 4, my temperature remains the same, and my volume is decreasing and my pressure is increasing. So again, it's isothermal. And finally, from 4 back to 1, P, V, and T are all changing, but it's an adiabatic process again. So it's important to have this complete cycle. So I go from 1, 2, 3, 4, back to 1, and so on, over and over. This temperature here, T1, is actually the temperature of the hot source, and T2 is the temperature of the cold sink. So as long as I have a temperature difference, I can use this cycle to extract work. The amount of work is equal to the area of this figure. If I calculate the area, that's how much work output I'm able to do from this heat engine. Another cycle is called the Rankine cycle. And this is the cycle used in steam engines. So So in this case, by steam engine, we mean a machine that uses a temperature difference to produce mechanical power using steam. So this is a bit more complicated than a Carnot cycle because we have a two-phase system. That water is transferring back and forth between liquid and gas phases. But a simple summary goes something like that. We have a pump that pressurizes the liquid. In this case, water. We have a heat source to produce steam. That steam is used to drive a turbine. And finally, the steam condenses back into water. Now this cycle is very important. It produces most of the electrical power in the world. Whether that heat source comes from nuclear energy or chemical energy or solar thermal, all those technologies use a steam engine to convert from mechanical power to electrical power.